In this video, we're going to cover section 1.19.1, photophysical processes. There are three important molecular states that must be considered when starting an analysis of a photochemical or photophysical process. They are the S0 or S0 state, the S1, and the T1. The S0 is the ground state of our reactant, R, and S1 and T1 are the electronically excited states of that species. Now, a state energy diagram, or Jablonski diagram, provides a compact working exemplar for displaying the relative energies of these important states. Higher energy singlet states and higher energy triplet states can also be included, but experimental experience has shown that excitation of these higher energy excited states generally results in deactivation to S1 and T1 faster than any other measurable process. In a state energy diagram, the y-axis represents the potential energy of the system. The x-axis has no physical meaning. The lines representing the singlet and triplet states are displaced for convenience and to avoid congestion. In state energy diagrams, it is assumed that the equilibrium nuclear geometries of both R and R star are similar, and that these geometries represent minima of R and R star. So let's look at an example of a state energy diagram. So as we just mentioned, in a state energy diagram, we highlight three important states: the S0 or S0, which is the ground state of the reactant R, and the electronically excited states S1 and T1, S1 representing the lowest singlet excited state, and T1 representing the lowest triplet excited state. What's also shown to the left and right of these states are the electronic configurations in the various orbitals. So again, the S0, we have a fully filled HO level. In the singlet excited state, we are promoting one of the electrons into the lowest unoccupied molecular orbital. And for the T1 state, the triplet state, we have a spin flip of that electron in the lowest unoccupied molecular orbital. Now, the other details that are being shown are with respect to transitions or processes, photophysical processes that occur between these states. Solid lines represent radiative transitions. These involve either the absorption or emission of a photon. And that's shown here. We have absorption between the S0 and S1. We have fluorescence from the S1 to the S0. And likewise, between the T1 and the S0, we can have a singlet triplet absorption, or we can have a T1 to S0 transition, which we refer to as phosphorescence. So we'll discuss the various radiative pathways for these electronic states. What's also shown are transitions that involve the loss of heat. So these are transitions that are considered non-radiative or radiationless because a photon is not absorbed or emitted. For example, if we have a radiationless transition from the S1 to the S0, we refer to this as internal conversion. So anytime we have a radiationless transition between states of similar multiplicity, that is singlet to singlet or triplet to triplet, we refer to this as internal conversion. Also, if we have a radiationless transition between a singlet state, the S1, and the T1, we refer to this as intersystem crossing. So in the next few slides, we're going to summarize the various photophysical processes that we often observe between S0, S1, and T1. In general, spectroscopic methods are based on transitions that occur between different energy states of molecules when they interact with electromagnetic radiation. These methods allow us to understand chemistry at the molecular and atomic level. In spectroscopy, We have two main types of transitions. We have what's known as formally allowed transitions and formally forbidden transitions. Formally allowed transitions are always allowed. Experimentally, these transitions are observed and often exhibit large intensities. For example, if the change in the total spin quantum number between two electronic states is equal to 0, we consider these formally allowed transitions. What this means from our earlier discussion is that transitions between states of similar multiplicity, that is, singlet to singlet or triplet to triplet, these are always allowed. However, transitions between states of different multiplicity, i.e. singlet to triplet or triplet to singlet, these are formally forbidden transitions. So formally forbidden transitions, these are weakly allowed via some mechanism, whether it be vibronic coupling or spin-orbit coupling. Experimentally, these transitions are observed, but they often exhibit small intensities. Now let's look at some possible photophysical, radiative, and radiationless processes that we typically observe for molecules. So the possible photophysical radiative processes, these involve the absorption or emission of a photon. The first is the spin-allowed singlet-singlet absorption of photons, in which your ground state molecule, S0, absorbs a photon of energy h nu to generate your electronically excited state, S1. This is characterized experimentally by the molar absorptivity of your reactant, epsilon. The second is the spin-forbidden singlet-triplet absorption of photons. That is, the absorption of a photon by the S0 or S0 state to give you an electronically excited state, which is T1. This is also characterized by the experimentally determined molar absorptivity. Because this is a spin-forbidden transition, we would expect the molar absorptivity for such a transition will be quite small. Third, the spin-allowed singlet-singlet emission of photons, that is, from the electronically excited state S1, returning to the ground state S0 with the emission of a photon, we refer to this process as fluorescence. And this is characterized experimentally by the rate constant K subscript F. And finally, the spin-forbidden triplet-singlet emission of photons, in which we have our lowest triplet state returning to the ground state with the emission of a photon, we refer to this as phosphorescence. And this, similar to the last example, is characterized by a rate constant K subscript P. And recall in our state energy diagram that we use solid vertical lines to represent these processes. Possible photophysical radiationless processes, these are processes that do not involve the absorption or emission of a photon. We often consider these transitions isoenergetic, meaning that the process occurs between two states of equal energy. The first example is the spin-allowed radiationless transition between states of the same spin. This is called internal conversion, and this is characterized by the rate constant K subscript IC. So although the transition is between states of equal energy initially, we cross from the S1 into the S0 at a very high vibrational level of the S0. And so following that transition, we have rapid vibrational relaxation from some higher vibrational level to the lowest vibrational level in the S0. And it's that vibrational relaxation that results in the loss of energy in the form of heat. Now, a spin-forbidden radiationless transition between states of different spin, this is called intersystem crossing, and also characterized by a rate constant, specifically K subscript ST. And in this example, we're going from the lowest singlet state, S1, to the lowest triplet state, T1. And again, it's initially isoenergetic, but then we have vibrational relaxation to the lowest vibrational level within the T1 electronic state, and it's that relaxation that results in the formation of some heat. And similarly, we have a spin-forbidden radiationless transition between the lowest triplet state and the ground state, for example, the T1 to the S0. This too is called intersystem crossing, but is characterized by the rate constant K subscript Ts to represent that T to S transition. And recall in our state energy diagram that we show these transitions with wavy arrows. Now, to determine which photophysical processes are most probable, we need to know the relative rates of all the processes that compete for the deactivation of these states. These rates are dependent upon the magnitude of the rate constants associated with these processes. The quantum yield, given as phi, of a photophysical process is the ratio of the rate of the process of interest over the sum of all the rates of the processes that lead to deactivation of the excited state. So as shown, phi is equal to the specific rate with respect to a particular process over the sum of the rates of all the processes that are potential deactivation pathways. In general, the sum is often described by the intensity of the absorbed light. And so we can write phi as being equal to the rate of that particular process of interest over the intensity of the absorbed light, the light that was absorbed by the sample. In this way, phi is used to describe the efficiency of photophysical processes. Now, to determine the fluorescence quantum yield, that is phi subscript f, we need to consider the following mechanism for the formation and decay of the electronically excited state S1. So, as we saw previously, our ground state S0, if it absorbs a photon, we can generate the S1. And we do so with a rate constant known as K subscript A, representing absorption. Following this absorption process, we have three competing pathways for that S1 population. We have a radiative pathway in which the S1 returns to the ground state S0 with the emission of a photon, known as fluorescence. We have a radiationless transition between S1 and S0 and the eventual loss of thermal energy, known as internal conversion. And we have the possible transition from the S1 to the T1 with the loss of some heat, which we refer to as intersystem crossing. So the time derivative for the concentration of S1, it can be written in the following way, where ds1 dt is equal to I abs, which represents the absorption process from the ground state to the first excited state, and three terms representing each of the deactivation pathways from the S1 back down to the ground state or to a low-lying triplet state. And as we saw in a previous video, IABS can be written in this way, where IABS is equal to the rate constant Ka and depend upon the concentration of the ground state. And we can equate the Ka term to the incident intensity, 2.303, the Moore absorptivity, and the path length of the sample. In practice, fluorescent measurements are performed by irradiating a dilute sample, that is, a sample with a low absorbance within the linear range of the Beer-Lambert absorption law. As well, it's irradiated with a continuous and intense beam of either ultraviolet or visible light. As a result, the concentration of S1 is generally small and constant. As a result, we can apply the steady state approximation to this particular expression. So ds1 dt, we can equate this to 0 because these conditions are consistent with the steady state approximation in that the concentration of this intermediate species S1 is relatively small, as well it is constant during the course of the reaction. So being able to equate the net rate of change of S1 to 0 allows us to express this equation to 0. Consequently, we can solve for IABS in terms of the sum of these three terms, these deactivation pathways, and we can also factor out the concentration S1, leaving us with the sum of the rate constants responsible for those three deactivation pathways. So the rate of fluorescence, epsilon F, we saw that this was equal to the rate constant Kf times the concentration of S1. So we can now rewrite the quantum yield of fluorescence in terms of these rate constants. So the quantum yield of fluorescence, which is equal to epsilon F, which now we know is equal to Kf times the concentration of S1, divided by IABS, which was equal to the sum of the rate constants responsible for deactivation of the S1 state times the concentration of S1. The concentration of S1 is going to cancel on both sides of this quotient. And so now we have our fluorescence quantum yield written in terms of the rate constants responsible for fluorescence and all the rate constants responsible for the deactivation of the S1 state. We can similarly write quantum yields for other processes using the same logic. So the quantum yield for internal conversion would simply be the rate constant for internal conversion over the sum of all the deactivation pathways. And similarly, the quantum yield for intersystem crossing would be equal to the rate constant for intersystem crossing, the S to T transition, over the sum of all the deactivation pathways. Lastly, we can also write quantum yields for various processes that begin from the T1 state. The only difference here now is that we have to include the quantum yield for intersystem crossing, which is responsible for populating the lowest lying triplet state, the T1 state, before we can use the same logic that we just described for deactivation of the T1 state. So the quantum yield of phosphorescence is equal to the quantum yield for intersystem crossing multiplied by this quotient, where we have the rate constant with respect to phosphorescence over the sum of the two competing pathways, that is phosphorescence and the triplet to singlet transition. Similarly, if we want to solve for the quantum yield for the radiationless transition from the triplet to the ground state singlet, again, we multiply first by the quantum yield for intersystem crossing, and then in our brackets, we have the rate constant for that particular process, again, over the sum of the two deactivation pathways, phosphorescence and the triplet singlet conversion. So in summary, we have shown that we can determine what the quantum yields of the various photophysical pathways are for a particular process. Now let's look at how we can determine what the sum of these rate constants are. That is the sum of the deactivation pathways for the S1 and the T1 state. Let's see how we can determine that experimentally. Using time-resolved emission spectroscopy, one can experimentally measure the lifetime of the singlet and triplet states. Similar to the relaxation time introduced earlier in the course, the lifetime is the time it takes for the reactant concentration to decrease to 1 over E, its initial value. And we denote this change as tau. So the singlet lifetime is denoted tau subscript S, whereas the triplet lifetime is denoted tau subscript T. Recall that for most photochemical reactions, the decay of the reactant concentration is consistent with a first-order kinetic behavior. In this way, we can write the concentration of the S1 state in a first-order exponential form, where the rate constant is now equal to the sum of the rate constants for each of those deactivation pathways. In this way, we can substitute in for this sum of rate constants with our tau S. So tau S, the singlet lifetime, is in fact the inverse of the sum of those deactivation pathways. Similarly, the triplet lifetime is also equal to the inverse of the sum of the rate constants for those deactivation pathways. So tau subscript t is equal to the inverse, or 1 over Kp plus Kts. And because we can experimentally determine what the singlet and triplet lifetimes are for excited state molecules, we can more easily measure the quantum yields associated with these photophysical processes. Therefore, the quantum yield of fluorescence can now be equated to the rate constant Kf multiplied by the singlet lifetime. And similarly, we can do the same type of calculation for the quantum yield of internal conversion, being equal to the rate constant KIC times the singlet lifetime, as well as that of intersystem crossing. And as we saw previously, we can also determine what the quantum yields for phosphorescence and the triplet singlet intersystem cross by multiplying the intersystem crossing quantum yield phi st and then the product of Kp times the triplet lifetime and Kts times the triplet lifetime. So as a result, if one experimentally measures the quantum yield of fluorescence, the quantum yield of phosphorescence, or the quantum yield of intersystem crossing, as well as the lifetimes of the singlet and triplet state, then one can determine the rate constants, Kf, Kic, Kst, Kp, and Kts. So these are the typical experimental measurements that one can carry out for photophysical processes. And from these measurements, we can experimentally determine what the individual rate constants are for a particular molecule. So let's look at an example of how one would calculate these rate constants using these experimentally determined values. So in this example, we're going to look at the photophysics of 1-chlronaphthalene at 77 Kelvin. 1-chlronaphthalene is a rigid aromatic system. It has a fluorescence quantum yield of 0.06 or 6%, a phosphorescence quantum yield of 0.54, a singlet lifetime of 10 nanoseconds, a triplet lifetime of 0.30 seconds. In addition, internal conversion is not expected to be competitive with fluorescence. And it's stated here that the rate constant with respect to internal conversion is expected to be less than 10% or 0.1 of whatever the rate constant for fluorescence is. With all this information, let's show how we can determine the rate constant with respect to fluorescence, internal conversion, intersystem crossing from the S1 to the T1, phosphorescence, and intersystem crossing from the T1 to the S0. So if we start with solving for the quantum yield for intersystem crossing from the S1 to T1, this is equal to 1 minus the quantum yields for both fluorescence and internal conversion, because the sum of these three quantum yields is equal to 1. So we're given the quantum yields for fluorescence, and we're given our estimate for the quantum yield for internal conversion based on this comparison. So if we use the value of the quantum yield for fluorescence, and we use that value to determine what the quantum yield is with respect to KIC, we end up with the following. We have 1 minus 0.06 minus 0.006. That gives us a value of 0.93, carry a single digit, rounding to give us 0.93. So our quantum yield for intersystem crossing from the S1 to the T1 is 0.93. And this is typical of rigid aromatic systems. They intersystem cross quite well. Now we can calculate what the quantum yield is with respect to the spin-forbidden T1 to S0, or the TS, and that's going to be equal to the quantum yield of intersystem cross from the S1 to T1 minus the quantum yield with respect to phosphorescence. We're given, or we can determine experimentally, and we're given in this expression what that value is. And so we can calculate based on the solution or result from the first calculation and what's given in the problem, we can calculate that to be 0.39. Now that we have our quantum yields for fluorescence, phosphorescence, intersystem cross from the S1 to T1 and intersystem cross from the T1 to S0, we can now calculate the rate constants. So using the expressions that we just presented on the previous slide, we can calculate KF by taking the fluorescence quantum yield, which is given in this question, divided by the singlet lifetime, which is also given in this question. And so the rate constant for fluorescence is equal to 6 times 10 to the 6 seconds to the minus 1. Because we now have a value for KF, we can use this approximation to calculate the rate constant for internal conversion. And so internal conversion, the rate constant for this process is expected to be less than 10% of KF. So it's going to be less than 0.6 times 10 to the 6 seconds minus 1. KST can be calculated in a similar manner. We can substitute in for the quantum yield of intersystem crossing from the S1 to T1 and divide by the lifetime, the singlet lifetime specifically. In doing so, we end up with a rate constant of 9.3 times 10 to the 7 seconds minus 1. The rate constant for phosphorescence can be calculated in a similar manner. Again, substitution into our expression from the previous slide, rearranging, of course, for the rate constant. We can take the phosphorescence quantum yield divided by the product of the intersystem crossing quantum yield and the triplet lifetime. We end up with a result of 1.9 per second. Similarly, we can calculate the rate constant from the T1 to the S0 state using a similar expression, substituting in for the quantum yield for that transition of 0.39, which we calculated previously, and dividing by the same product, the product of the intersystem crossing quantum yield and the triplet lifetime, we end up with a rate constant of 1.4 seconds to the minus 1. So again, using the experimentally determined lifetime values, that is the singlet and triplet lifetimes, as well as quantum yields for fluorescence and phosphorescence, we can determine the rate constants for these photophysical processes. So all the photophysical processes that we've discussed so far are unimolecular in nature, meaning they don't involve collisions with other molecules. It's simply the deactivation of the S1 or T1 states as they return to the ground state, the S0. The last part of this video, we're going to look at one additional process which involves a bimolecular event, that is quenching. So the shortening of a singlet or triplet lifetime by the presence of another species is called quenching. Quenching is a bimolecular process. It may be a desired process, such as in energy or electron transfer, or it may be an undesired side reaction that decreases the quantum yield of a photochemical process. Quenching studies are often performed by monitoring changes in the excited state emission that is involved in the photochemical reaction as a function of the concentration of a quencher. And we use the symbol uppercase Q to represent that quencher concentration. In collisional quenching, a collision occurs between the quencher and the excited state of interest, S1 or T1. The result of the collision is the removal of energy from the excited state molecule and its conversion to the ground state. For example, the decay of S1 in the presence of a collisional quencher is shown, where our first excited singlet state interacts with a quencher molecule in a bimolecular collision with a rate constant K subscript Q, and the result of this collision, we end up with our ground state molecule S0, the quencher usually unaffected, but during the process, the energy associated with the S1 is lost in the form of heat. So if bimolecular quenching is a potential deactivation pathway for the S1 state, then the steady state approximation for the concentration of S1 will change. It now becomes IABS minus the three original terms associated with fluorescence, internal conversion, and intersystem crossing, but now we have a fourth term representing collisional quenching. And so if we solve for IABS under steady state approximation conditions, we're left with the sum of these four terms, including four rate constants, each including the concentration of S1. Only the last term, our new quenching term, also includes the quencher concentration. So if we factor out S1, we're left with the summation of the following four terms. Now, the quantum yield of fluorescence in the presence of a quencher will be equal to the following, where it's Kf times S1 all over the sum of the four possible deactivation rate constants, including the quencher concentration term for the bimolecular process, all multiplied by S1. We then simplify this expression by canceling our S1s in both sides of the quotient, and we're left with the following expression, where we now have the fluorescence quantum yield in the presence of a quencher being equal to the rate constant of fluorescence all over the sum of all the competing pathways, that is fluorescence, internal conversion, intersystem crossing, and our new term, Kq times the concentration of quencher. Now, if we want to take the ratio of fluorescent quantum yields without and with quencher present, we can do so in the following way. So again, if we take the ratio, we're taking the quantum yield of fluorescence in the absence of quencher, that's this term. And if we divide by the fluorescence quantum yield with quencher present, that's like multiplying by the inverse of the expression that we just defined. In doing so, we get some simplification, we get cancellation of Kf, and we're left with the following expression. Now we can break up the numerator into two terms using a common denominator such that this ratio of fluorescent quantum yields can be equated to 1 plus KQQ all over the sum of these three rate constants, and that's shown here. In doing so, we can further simplify the 1 over the sum of these three rate constants with the singlet lifetime, which is typically also called the fluorescence lifetime in the absence of quencher. Nonetheless, this expression is known as the Stern-Volmer equation, and it's a very useful equation for determining what the rate constant for a quenching process is, as we'll see on the next slide. So for the Stern-Volmer equation to be consistent with experiment, a good linear fit to the experimental data will be observed for a plot of the ratio of the fluorescent quantum yields in the absence and presence of quencher against the quencher concentration if there is a strong association between these two variables. The slope of the linear fit provides a measure of the quenching rate constant, K subscript Q. The slope is actually a product of that rate constant and the singlet lifetime. And the singlet lifetime can be measured independently using time-resolved emission spectroscopy. Lastly, since the fluorescence quantum yield is proportional to the rate of fluorescence, which determines the fluorescence intensity, and the fluorescence lifetime, the following ratios can also be used to determine the quenching rate constant. So as shown, we've been looking at the Stern-Volmer expression with respect to the fluorescence quantum yields in the absence and presence of a quencher. We can equate that ratio to a ratio of fluorescence intensities or fluorescence lifetimes, again, in the presence or absence of quencher. In particular, if we look at the ratio of the fluorescence lifetimes in the absence and presence of quencher, if we substitute that in for the ratio of the fluorescence quantum yields, we end up with this expression. If we divide through on both sides by the fluorescence lifetime in the absence of quencher, we end up with the following expression. So experimentally, if one has access to time-resolved emission spectroscopy, you can use this form of the Stern-Volmer expression to determine the quenching rate constant directly. Otherwise, if what's available is a steady-state fluorescence spectrometer, then you would use a ratio of the fluorescence intensities in the absence and presence of quencher to determine the product of the quenching rate constant and the singlet lifetime. So if you have any questions on the material that was discussed in this video on photophysical processes, don't hesitate to email me. Thank you.